Right, so Honors Algebra 2, with all the snow days and everything, and with your quiz being this Friday, just to let you know, I will not be here this Friday, so in place of that, I'm going to take you through just a few extra examples for graphing rationals. And it says day 1, this is really more of day 2 where you're doing stuff by hand. So I just wanted to real quick kind of walk you through a few of these just to give you some extra examples to look at today. And that way, if you needed some extra practice going into the quiz, here you go. So when you're asked to determine the domain of a rational function, basically what that's kind of asking for is the domain restrictions, and then kind of using those to then put your domain into an interval notation. For example, on number 1, if x cannot equal 7, but it can equal anything else, then you would say from negative infinity up to 7, in union with from 7 up to infinity. And then on something like number 3, then, if you factor, you get x minus 2 multiplied by x minus 5. In other words, for this particular problem, x cannot equal the number 2 or the number 5. Then you would just have an extra interval. You'd just say negative infinity up to 2, in union with from 2 up to 5, in union with from 5 up to positive infinity. So really all you're doing is kind of separating from negative infinity up to positive infinity by whatever your domain restrictions are. So let's go through, let's kind of take a look at some of these examples. I'm going to skip the ones where they've already got them factored for you because those should be hopefully pretty easy. Let's take a look at a few where they're not factored. So on number 7, we've got x plus 2 multiplied by x plus 3 for our denominator. I'm just going to go through and factor everything. So let's see, on number 8, x plus 4, x minus 4. Denominator would be x minus 4, x minus 1. And then for our last one here, you're going to have x minus 1 multiplied by itself, x minus 1. And then x plus 2 multiplied by x minus 1 there for your second factor. Okay, so first thing let's go through and simplify as much as we can. Let's see, this x plus 2 will simplify with one of these x plus 2's, so you'll still have an x plus 2 in your numerator. Here you're going to have your x minus 4's divide out. Here you're going to have your x minus 1's divide out. So going through and kind of talking about where you've got holes at. For the first one, it looks like you're going to have a hole at negative 2. And then if you put negative 2 into your function to see where that hole actually is, you get negative 2. Let's make that a little bit neater for you guys. So let's see, we have negative 2 plus 2 over negative 2 plus 3, which ends up being 0 over 1. So your y value of your hole is going to be 0. For this one, it looks like you've got a hole at 4. And then let's see, that gives you 4 plus 4 for your numerator over 4 minus 1 for your denominator, which becomes 8 over 3. And then it doesn't look like that's going to reduce, so we'll just say 8 over 3. For this last one here, it looks like you're going to have a hole at positive 1. So then putting that into your remaining function, 1 minus 1 over 1 plus 2. Looks like 1 minus 1 is 0. 1 plus 2 is 3. So 1 comma 0 there is going to be your hole. Okay, horizontal asymptotes. Remember, for horizontal asymptotes, you need to look at your degree of your numerator and denominator. Here, the degree of my numerator is a 1. The degree of the denominator is a 1. They're the same, so I look at my coefficients, which is going to be 1 over 1. So my horizontal asymptotes through y equals 1. On number 8, if you notice, you also have degrees of 1s as well as coefficients of 1s. So once again, horizontal asymptote, there's a 1. And then same thing on the last one here. Let's say it was something slightly different. Like let's say you had maybe something like 2x plus 1 over x minus 1. Then what you'd look at, since your degrees are the same, now your leading coefficients are 2 over 1. So in that case, you'd have a horizontal asymptote at y equals 2. And then later on, we'll look at if they're different, kind of what will happen there. We'll do that actually by looking at some graphs of some different ones. But for right now, just kind of understand that if they're the same, looking at your leading coefficient. Okay. Let's see. Next thing, let's go through and do vertical asymptotes. Vertical asymptotes are whatever factor is left in your denominator, set that equal to 0. So in this case, x is equal to negative 3. For this one on number 8, x would be equal to positive 1. Remember, it's going to be the opposite since you're setting it equal to 0. And then for this last one, it's going to be through negative 2. Notice that for vertical asymptotes, we're not saying x cannot equal. That would be a domain restriction. Instead, we're saying a vertical asymptote, which is the equation for a line instead. All right. Last thing for each of these, before we actually look at some graphing. So for roots, those are whatever factors are left in your numerator. So for this one, you'd have a root at negative 2 comma 0. Then you might see kind of a problem with that, because if you notice, it says there's a hole at negative 2, 0. And there's supposed to be a root at negative 2, 0. Hole trumps root. In other words, for this first one, there are no roots. So you could just write none or not applicable. Any of that would work. Let's see. For number 8, we've got x plus 4. So that would give us a root at negative 4 comma 0, which if you notice is different from our hole, so we're good there. For number 9, very similar to number 7, if you notice, your root should have been at 1 comma 0, but you have a hole at 1 comma 0. And so in this case, just like on number 7, there are none or not applicable, or however you'd want to write that. Okay, so there's kind of the basics of kind of looking through each of those different key characteristics. I guess one thing that we didn't include in any of these was the y-intercept. So if we want to go through and talk about y-intercepts, it's not too hard to do that. For y-intercepts, you just look at whatever your remaining kind of constants are. So for this one, 2 over 3, so you'd have a y-intercept at 0 comma 2/3. For this problem on number 8, here you've got a 4 over negative 1 left over. So your y-intercept there would be 0 comma negative 4, being that you took 4 divided by negative 1 and got negative 4. Something else you guys can do too, keep in mind y-intercepts have to have an x value of 0. So if you can't remember how to get the y-intercept just by looking at the equation, just put in 0 for x and that'll get you the same thing. So let me show you that on number 9 if you needed to. And so if you didn't already see that you had negative 1 over 2 was negative 1/2, then what you could do is put 0 for x, 0 minus 1 over 0 plus 2. That gets you the exact same thing, negative 1 over 2. And so then you've got your y-intercept at 0 comma negative 1/2. Okay, and I think that was pretty much everything we looked at as far as with regards to the characteristics. So let's take a look at some graphs now. So number 10, we're going to find all the key characteristics or key features of the following rational function and then graph it. So number 10, once again, let's kind of start this one by factoring. So x minus 2 over x plus, let's see, 1, x minus 3. So looking at our factors, there's not any factors which are going to divide out. So for holes on this one, there are none. Let's now look at our horizontal asymptotes. If you notice for this one, our degrees are different. Your numerator has a degree of 1, the denominator has a degree of 2. What you can kind of think about this as is if your numerator would have kind of a 0x squared in front of it, then they would have the same degree. You'd put 0 over 1. In other words, your horizontal asymptote is through y equals 0. Or if you just remember that if the degree of the numerator is less than degree of the denominator, that's y equals 0, that works too. For domain on this one, let's go ahead and let's set an interval notation. So we cannot have x equal negative 1 and x cannot equal 3. So for our domain, we would say from negative infinity up to negative 1, and union with from negative 1 up to 3, and union with from 3 up to positive infinity. Let's see, for vertical asymptotes, since there were no holes, basically your domain restrictions become your vertical asymptotes. In other words, you're going to have vertical asymptote through negative 1 and a second one through positive 3. Last thing that we've got to look at here for our roots, we look at x minus 2. That would give us a root at 2 comma 0. We also can look at our y-intercept. For our y-intercept, we've got negative 2 and negative 3 as our constants there. So our y-intercept for this one would be at 0 comma 2/3. Be careful with that, not negative 2/3. Negative 2 over negative 3, positive 2/3. So let's go through and graph some of this stuff. Let's see, for vertical asymptotes, x equals negative 1 was one of those. So something kind of like this. We also had x equals 3, so something kind of like this. And we also had a horizontal asymptote through y equals 0. It's right on top of your x-axis. And here's kind of the interesting thing. Note that just because you have a or a horizontal asymptote through y equals 0, you can still have a root. For instance, this one has a root at 2, 0. And then a y-intercept of 2/3. So this must be 1 with 3 sections, where the middle of our graph is kind of going through this way.
Students, if you're taking the ACT test
At this point, we're going to have to start to test some points to kind of see where the rest of our graph is. The first point that I'm going to test is going to be at +4. So at x equals 4, let's see what our y value is. We'd have 4 minus 2 over 4 plus 1 multiplied by 4 minus 3. That ends up being 2 over 5 multiplied by 1. So 2/5, in other words. At +4, I'm going to go up to about 2/5, which means my graph is going to be decreasing here, something kind of like this. And then I've got one more test point to kind of look at. For this next one, I need to test a point to the left of this vertical asymptote. So let's test it through x equals -2. So at -2, you're going to have -2 minus 2 over -2 plus 1 multiplied by -2 minus 3 becomes -4 over -1 multiplied by -5. So a positive, or actually a negative, it's going to be a -4/5 is basically what that's going to look like. So -4/5 is going to be at -2, so about right in here. And then here's the rest of your graph. Some things to kind of point out. If you notice, all of our intervals are decreasing. If you notice here, we're decreasing. In the middle, we are decreasing. The last end, we are decreasing. And so your graph for a rational function should either be decreasing for the entire graph or increasing for the entire graph. But there should be no increasing and decreasing. And remember, that's looking from left to right. So even though it looks like over here on the right side that you're going up, keep in mind going from left to right, you are starting up and going down. Let's take a look at one more that would be kind of similar. Actually, number 12 is too similar. Let's look at 11, kind of how to graph it. So number 11, first thing let's do is factor it. We get x plus 4 multiplied by x plus 2. Make sure that this is all separate from all this other stuff we did. And then we've got x squared minus 4 becomes x plus 2 multiplied by x minus 2. Now, unlike the last problem, this one does end up having a hole because your factor of x plus 2 is going to cancel. So you're going to have a hole at -2. And then if you put in -2, you get -2 plus 4 over -2 minus 2 becomes 2 over -4, or a -1 over 2. Let's see. For the next part here, let's look at our horizontal asymptotes. Why not? So for horizontal asymptotes, your degrees are the same here. So you look at the leading coefficients. 1 over 1 is y is equal to 1. With that being said, guys, please make sure you're looking at leading coefficients. For horizontal asymptotes, too oftentimes I see people put a degree of 1 over 1 as opposed to a coefficient of 1 over 1. So when you're looking at those, once you notice that the degrees are the same, you have to look at leading coefficients. For domain, keep in mind domain needs to be everything from the original function, meaning that the x plus 2 and x minus 2 means that x cannot equal 2 or -2. And then if you want to put that in interval notation, negative infinity up to -2, -2 up to 2, and 2 up to positive infinity. And then just your union with in between. For vertical asymptotes, any factors left in your denominator. So that x minus 2 would tell you that at x equals 2, you've got a vertical asymptote. And then for roots, let's see, what was left in our numerator was a +4. So at -4, 0, there's going to be our root. Let's see, for y-intercept on this one, you're going to have -8 over -4. So for your y-intercept, that's going to be through 0, -2. All right, let's do some graphing now. So the first thing, horizontal asymptote through y equals 1. Here that is. Next thing, let's look at vertical asymptote through x equals 2. So here that is. Let's see, holes, I've got a hole at -2, comma -1/2. Make sure that when you graph holes, guys, that you leave those as open points. Let's see, I've got a root at -4, 0, so here that is. Got a y-intercept at 0, -2, so here that is. So you really get kind of a nice picture of your graph on the left side here, going through those 3 points. So looking at the right side, I don't have anything. So again, I'm going to have to test a point. Make sure you pick any of these x values to the right of that that vertical asymptote. So for this one, I'm going to test x equals 3. So when I put 3 into, I would use your remaining function to test your point. So 3 plus 4 over 3 minus 2 becomes 7 over 1, or just 7. So 3 comma, and it's going to way up here, 7. Here's your last point, which tells you your graph should be up here on the top right. Once again, notice that you are decreasing for this entire graph, so you are decreasing over here on the left side of your vertical asymptote. You're also decreasing to the right side of your vertical asymptote. At this point, guys, that's pretty much it as far as graphing goes. If you wanted to try 12, you could pause the video and work through that one. It would be very similar to number 10 that we worked up here at the top. Also, if you'd like some more practice here with just identifying horizontal, vertical asymptotes, holes, roots, y-intercepts, there's a few problems right here, so if you wanted to pause the video and try those, here those are for you. And then there's one more domain restriction one. If you wanted to try number 2 at all, you could. So guys, just as a reminder, you do have a quiz on Friday. That is this Friday, which is 2/22. So please be sure you're ready for that. On your quiz, you will have problems that refer to graphing, as well as problems that refer to solving. I think I've got 2 solving for you. I've got a few with transformations, and then I've got at least one which is a full-on graphing, meaning identify all the characteristics and provide a graph, kind of like what we did just now with numbers 10 and 11 on this kind of extra practice. I am planning to post this extra practice for you. I don't know that I'll have enough time to get a key up for you, but at least you've got this video to refer back to if you've got any questions on how to do any of this stuff. And yeah, have a great day, guys. Have a great weekend, and I will see you back on Monday.